Also, with the geometric series, we have this thing called the sum to infinity, also known as the limiting sum. Now, it's important to note that we will only get one of these if the magnitude of the ratio is less than 1. Now, the reason for that. Remember we said that the geometric series, if we were to plot each term on a graph, it would look like an exponential curve because our general term is AR to the n minus 1. The variable is in the power or the exponent. Now, if that power is less than 1, let's say it's a half, well, that's like saying to the power of negative 2. So it's actually our negative exponential, which comes down, and as the numbers get bigger and bigger, it is approaching, well, the basic one approached the x-axis. So because it comes down, another word for this is it converges. The series converges to a limit. Graphically, that's our horizontal asymptote. So let's go back and work out this sum to infinity, a formula for it. So that's what I'm saying. Well, r to the power of n, as n gets bigger and bigger and bigger, that comes down to 0. Our asymptote is going to be the axis. So we know it's approaching 0. So the sequence, there's that word, converges to 0. Substituting that into our formula. So the limit as n approaches infinity of sum to n will be the limit as n approaches infinity of a, 1 minus r to the power of n over 1 minus r. But we just said r to the power of n will be approaching 0. So that becomes a on 1 minus r. So there's our formula. The sum to infinity is a on 1 minus r, but again, it only works if the magnitude or the size of the ratio is less than 1. Our series converges as opposed to other series which would diverge. So the first example is simply this question. Does this series have a limiting sum? So when they ask something like this, they're basically seeing if you understand the condition. So we have a look at our common ratio, 4 over 56. And to double check, 2/7 divided by 4 is also 4 over 56. Well, equivalent to it. And that is less than 1. So yes, it does have a limiting sum. A half plus a quarter plus an eighth and so on. Well, the first term is a half. Our ratio is a half as well. So it's going plus ... implying there's an infinite number of terms, but we can come up with a finite answer. Our sum to infinity will be a on 1 minus r, or half on 1 minus half, which is 1. We've seen this sort of question before. Write 0.36 repeater as a fraction, and we saw a very quick way of doing it. I suppose a more correct way of asking this example would have been to say, by expressing 0.36 as an infinite series. Now, if they say that, you have no choice. You've got to use this method. So 0.36 repeater would be 0.36 plus 0.0036 plus 0.000036 plus 0.00000036 and so on and so on. So the first term is 0.36. Our common ratio, 0.01. Sum to infinity, a on 1 minus r, 0.36 on 1 minus 0.01. Well, that's 0.36 on 0.99, but we don't normally write fractions with decimals on decimals. So tidying that fraction up, it's 36 on 99. Simplifies to be 4 on 11. Okay, well, to finish off this topic, a couple of exercises, 1H and 1I.